Hi everyone, hope all of you guys are doing well. So let's go ahead and get started with our chapter 16, which is going to be our first chapter. Okay, and let's see. Okay, so what are we going to learn in this chapter? It is kinetics. Kinetics is the first chapter. We're going to learn about the rates and mechanisms of chemical reactions. So we're going to focus on reaction rate. So we have learned about the reactions. Basically, reaction is something you have a reactant and it goes to a product, right? So we're going to learn what is the reaction rate and how can we express the reaction rate. And then we're also going to learn the rate law and its components, and then integrated rate laws where we can see how the concentration changes over time, and some theories of chemical kinetics, reaction mechanisms, meaning the steps from reactant to product, and then finally catalysis, how can we speed up a reaction. So these are the beautiful chemistry that we're going to learn in this chapter. Okay, now let's look at with this diagram how does a faster reaction looks like and how does a slower reaction looks like. Let me quiet this guy, or it's going to be trouble. Okay. Now in the first one, you can see there are some purple circles going to green circles. Now the very first one over here, you have lots of reactants, and this is the time. As the time progresses, what's happening? So the reactants are becoming products, green, and with the time, most of the reactants, which is the purple circles, have become green. Okay, only one of the reactant species left. So we can say during this time period, it is a faster reaction. Reaction has proceeded very fast. And then let's look at the other reaction. The second one, excuse me, where we start with some blue spheres. Blue becoming yellow is our reaction. Okay, so with the same time, what do we see here? We have more of the yellow, more of the blue ones left over, right, with the same time period. So we have some of the blue has turned to yellow, but there are more blues left over, meaning that is a slower reaction. So with the same time period, we can have faster reactions and we can also have slow reactions within the same time period. Okay, so we should be able to find out or calculate what is the rate of a reaction. So that is what we are going to learn. So understanding what is a faster reaction and a slower reaction is beneficial for us. Okay, and these are some wide ranges of reaction rates. Now the first one, you can see it's an explosion, and it takes only a second to do a explosion, which has a very high reaction rate. And same thing like a neutralization reaction, like when you put acid and base together, within seconds the neutralization acid react with base to give you a salt and water. And then you can see some fruits ripening. So it can take, because it involves some enzymes and it is a little longer process, maybe it can take few weeks to few months, right, ripening of a fruit. And then you can see a baby is drinking milk, and then baby is holding by his grandma. So baby becoming grandma, right? So that also takes about several decades. That you can see here the growth of a baby to become an old person. So that is about several decades. And then you can also see a formation of a forest. Now it also sometimes can take millions of years, right? So there are wide variety of reaction rates that we experience in our day-to-day life. All of these reactions are happening and they have a certain rate. Now this tells us some of the factors that influence reaction rate. So what are the factors that influence a reaction rate? Particles must collide in order to react. That's why mostly when we are doing a reaction, we put a stir bar, or you take a spatula and you stir the reaction mixture, because we want the particles to collide. They have to collide in order to react. And also, the higher the concentration of reactants, so compared to a dilute reaction mixture, the more concentrated reactants, the greater the reaction rate. So what happens when you have more reactant molecules? Higher concentration of reactant particles allows a greater number of collisions. The more particles you have, greater number of collisions, so that would increase the reaction rate. It also matters the physical state. So the physical state could be a solid, gas, or liquid. If you put two solids together, it might not give us a higher reaction rate. But if you dissolve it in water to make it a liquid or aqueous solution, so that would, because it's in the now liquid state, they can collide them, right? So the physical state of the reactant influences reaction rate, because substances must mix in order for particles to collide. And then the temperature. Temperature is also a greater fact, because when you increase the temperature, motion of the particles, kinetic energy increases, so we can have a greater reaction rate. Okay. Excuse me. Sometimes we mix two reagents together at room temperature, you stir it, nothing would happen. But you increase the temperature, you heat it up, you can see, excuse me dear, you can see the particles are moving, and then reaction rate increases. We can get the product done at a faster rate and at a small time period. Okay, higher temperatures particles have more energy and therefore collide more often and more effectively. Excuse me. Now, how do we express the reaction rate? So this is how normally we express the reaction rate. Reaction rate is measured in terms of the changes in the concentration of reactants or products per unit time. So the changes in concentrations of reactants or products per unit time. At a certain time period, what is the change in reactants or the products? Let's say we have a general reaction, A goes to B. We measure the concentration of A at time 1 and time 2. So the rate is expressed as change in concentration of A over change in time. How do we find the change in concentration of A? So we have a certain time period, let's say T1 and T2. So at T2, what is the concentration of A2? And T1, what is the concentration of A1? So when you get the difference of these two, A2 minus A1, and you divide it by T2 minus T1. Okay, so A2 minus A1, T2 minus T1. So this is equal. Concentration A2 minus concentration A1. So that's the change. So we give that as delta A. So the difference is given as delta A. And T2 minus T1 is the difference in temperature delta T. So rate is basically delta A over delta T. Concentration of A2 minus concentration of A1. Okay. I'm going to check something here. I think it's negative. Okay, so here this is going to be negative, because now if you start a reactant with A and a certain time period, it becomes concentration A2. Which one is bigger, A2 or A1 bigger? A1 is going to be bigger, because A1 is what you started with. Right now you have A2, so A2 is less than A1. So the difference, concentration A2 minus A1, is going to be a negative term. Okay, and delta T would be the time period or the change in time. So in this case, the rate we can express as concentration of A over delta T. And for here also we need to have a negative sign, because the reactant concentration is going to be, since it's going to decrease, it's going to be negative delta A over delta T. Okay? Okay. Excuse me. Now this example over here, or the graph, shows us three types of reaction rates for the reaction of ozone and C2H4. C2H4 is ethylene. So C2H4, it's a gas. So C2H4 is a gas. I'm going to put some parentheses here. Plus ozone gas. Okay. Giving you C2H4O, which is also a gas, plus oxygen gas. Okay, so the three types of reaction rates. So now let's look at this graph and see what are the three types of reaction rates. So ABC, it tells us about the rate type as average. So where is A? A is here. You see here, from 0 times 0 to times 60. Rate type, it's an average from 0 to 60, so average time. So line A represent rate as average. Oh, so the rate is given as 3.5 into 10 to the negative 7, that is the average rate. Or we can find out the average rate from 0 time to 10 seconds. So 0 and then the 10 seconds here. So what you do is you make a straight line from here to here, and you can find out the average rate for 0 to 10. Or if you want to find out average rate from 50 to 60, so here's the 50 and here's the 60, and you draw a line, and then you can find out what is the average rate. Concentration of ozone over time period. That's how you find average rate. So since the time periods are different, you can see different rates for the average. And also that is one type of reaction rate. Or we can find out the instantaneous rate, meaning at one instance, what is the rate of that reaction. You pick one point, let's say at 35 seconds or 35 seconds. So you draw a tangent parallel to this point, and then you find delta ozone concentration from this axis, and from the y-axis you find delta T, temperature. Okay, and delta ozone over delta T, this is the time. You find these values and you can find out the instantaneous rate. That is the second type. Average rate, instantaneous rate, or the initial rate. Initial rate is calculated here at the very beginning. As soon as you mix the reactants, what is the rate of the reaction? So this is A and this is B, this is C, this is D, and then E over here is the instant initial rate. And how do you calculate the initial rate? These rates calculated through spectroscopic instrumentation. So we can find out from spectroscopic data what are these initial rates. And initial rate is what we're going to be using throughout our this chapter to find out the reaction rates. Okay. And these are the concentrations of ozone with time, how it changes. So you can see that it goes down, concentration of ozone, because ozone is one of your reactants. So at the beginning 3.2 into 10 to the negative 5, and as the time increases, ozone reacts and concentration of ozone decreases. Now it's 1.1 into 10 to the negative 5. Okay, So there are three types of reaction rates. What's important for us is the initial rate. Okay. Plots of reactants and product versus time. Now this plot shows us what is happening as the reaction proceeds. So the rate, now let's say we have this reaction over here. C2H4 plus ozone giving us C2H4O plus oxygen. So ethylene and ozone are our reactants. As the reaction proceeds, what happened to the reactant? So this is C2H4. You started with a higher concentration and it decreases. So this red curve shows us it decreases. So if you write the rate in terms of C2H4, what is happening? It is decreasing. So it's a negative value. Negative delta C2H4. So for the reactants, it decreases, it's negative over delta T. That's how you write the rate. And in terms of ozone, ozone also a reactant. So delta ozone, again that's going to be a negative sign over delta T would be the rate. And also we can write the rate in terms of products. What's happening? At the beginning, so this is oxygen concentration. At the very beginning, we have not made any oxygen. Now when you add C2H4 and ozone together, it starts reacting and oxygen concentration increases. So this blue line shows us that the oxygen concentration increasing. So if you get the rate for the oxygen and excuse me, the other product C2H4O, when you write their rate equation, that is going to be positive since we are going to make them. So C2H4O over delta T, similar to oxygen concentration over delta T. Remember, the reactants are going to be negative and the products are going to be positive. Okay. Now here's another example. So H2 plus I2 giving us 2HI. You see here? H2 plus I2 giving us 2HI. Excuse me. Here again hydrogen and iodine concentrations are decreasing. That's why you are seeing it over here. Now the ratio is H2 plus I2 giving you 2HI. Each 1 mole of hydrogen and 1 mole of iodine that reacts, 2 moles of hydrogen iodide produced. So you can see that the curve for hydrogen iodide is increasing more because of the molar ratio 1 to 2. So we have to represent this in our rate law as well. Since hydrogen iodide increases twice as fast as hydrogen concentration decreases, it would be the same for the iodine as well. So when you write the rate, this is how we're going to write the rate. So again, hydrogen and iodine, they are reactants. For reactants, it's always going to be negative since we are decreasing the concentration of reactant. So negative delta H2 over delta T equals, in terms of iodine, there would be again negative since it's a reactant, concentration of iodine over delta T. And then for the hydrogen iodide, since the molar ratio is 1 to 2, so you can remember the coefficient goes to your denominator. And this is going to be positive in terms of rate since we are making more of the hydrogen iodide. So 1 over 2 delta hydrogen iodide concentration over delta T. Okay. And similarly, if you want to relate this in terms of hydrogen iodide over delta T, if you want to get rid of this 2, 1 over 2, you can basically you multiply this side by 2. Okay, so delta Hi over delta T would be equal to negative 2 delta H2 over delta T equals negative 2 delta iodine over delta T. Either one is correct. Okay. Now we can show this in a generalized term like this. General form of reaction rate. let's say you have AA plus BB, and this simple A's, these little A's, little B's, little C, D, and they represent your stoichiometric ratio or the molar coefficient. So let's say A plus B giving you C plus D. And how would you write the rate for this reaction? So the rate equals, and the coefficient for A is little a, so 1 over A. And remember, since A and B, they are reactants, it has to be negative. So from my laptop, when I transfer it to the iPad, some of the signs disappear. So I need to write them again. Okay, that's what I'm writing. So the negative has to be there. And then again, for the B, also a reactant, so it has to be negative. 1 over B, negative 1 over B, delta B over delta T. Normally we put concentrations in parentheses, equal. So the C and D is going to be positive because they are going to be your products. So if you have this coefficient like that, how would you write the rate law? Negative 1 over small a, delta A over delta T, equals negative 1 over small b, delta B over delta T. So these are your coefficients. It's not the negative sign. Okay. And then you have a C and D, they are products, so they are going to be positive. 1 over C, delta C over delta T, 1 over D, delta D over delta T. That is a general form of reaction rate. Excuse me. Okay. Let's look at this sample problem now. Expressing rate in terms of changes in concentration with time. Hydrogen gas has a non-polluting combustion product, water vapor. This gas is used as a fuel aboard the space shuttle and in earthbound cars with prototype engines. So hydrogen gas plus oxygen giving us 2 water molecules. Hydrogen gas plus oxygen giving us 2 water molecules as gas. Express the rate in terms of changes in hydrogen, oxygen and water with time. Remember how we can express it? Now this is a balanced equation. 4 hydrogens over here, 2 times 2, and 4 hydrogens here, 2 oxygen here, and then we have 2 oxygens in your product as well. So how would we write the rate? Remember, we take into consideration the coefficients, 2 right there, and for the oxygen 1 and 2 for the water. So the rate, I'm going to go ahead and write it down over here. Since it's for the reactants, it's going to be negative. So negative for the hydrogen. Remember the coefficient is 2, 1 over 2 delta hydrogen over delta T, which is similar to oxygen, since coefficient for oxygen is 1. Again, since oxygen is a reactant, negative delta oxygen O2 over delta T equals, and then the water molecule. Water molecule is your product, so that's going to be positive in terms of rate. So, and we have a coefficient 2, 1 over 2 delta concentration of water over delta T. So express the rate in terms of changes in hydrogen, oxygen and water with time. So that is how you express the rate. Okay. Like this. Let me go ahead and increase the missing components. So rate equals, this is negative O2 over oxygen, and this is also negative. This is the same thing I did with you in the previous slide. See, oxygen and hydrogen, they are negative since they are reactants, and we also took into consideration the coefficients, and then the water, the product is positive. Okay, and then we have another question to ask or answer. The next question, once you express those, the B, when oxygen concentration is decreasing at 0.23 moles per liters per second, what rate is water increasing? When oxygen is decreasing at 0.23 moles per liters per second, what rate is water increasing? Now we are going to relate oxygen with water. So to do that, we take these two. We use concentration of oxygen over delta T and this. So we take this relationship. Okay, so let's see how we're going to do that. Okay, calculate the rate of change of water is what we are going to do now. Now we use these two, oxygen and water. So we put them together side by side. Half oxygen concentration of water over delta T, remember that is positive, equals concentration of oxygen, we are missing this part, negative. I'm going to go ahead and put the missing parts, oxygen, delta T equals. Now we were given the change of concentration of oxygen is given as 0.23. Since it's negative, its oxygen concentration is negative, you put it as negative 0.23 moles per liters per second. Okay. Now we're gonna, there is 2 here, but what we want is change in concentration of water. Okay. So this 2 that you have in denominator has to go to the other side and it will become a multiplication. So 2 times 0.23 moles per liters per second. Okay, so 2 times 0.23 is 0.46 moles per liters per second. So as the concentration of oxygen 0.23 moles per liters per second, and then the concentration of water increases in 2 times of that, which is 0.46, right? Because that is what we also have in our equation. You see here, 1 mole of oxygen react to give you 2 moles of water. As the oxygen concentration decreases, water concentration increases 2 times. Okay, the rate increases. This decreases and water rate increases. Okay, so it represents in our rate as well 0.46 moles per liters per second. Okay, so here I am going to put something else. Okay, so here we oxygen concentration is negative because it's decreasing, and we also have this negative part. So negative, this two negatives will become positive. Okay, that's how you get the positive answer at the end. Okay, I will stop this part here and I will explain the rate law in the next video. Okay, bye for now.